Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I want to go over the three-moment equations. The three-moment equation approach helps you solve and find the reactions at the supports for statically indeterminate beams and frames. So what is the idea? Well, the derivation is found and it's going to take some time. It's not really that important. The most important part is to say that suppose I have a beam and we'll go over a detailed example, but here I'm going to say, suppose I have like a pin, a roller, another roller, and maybe that's fine. Okay. And then when I draw there have some weights here. And let's say I'm going to draw the bending moment diagram. And I got something that looks like that. Whatever. I'm going to call this as point A, B, C. And I'm going to show you how we write the equation at B. So from here, I'm going to refer to point A as the left in writing the equation, but then we are going to call that MA, or we are going to refer to them as ABC, but I'm going to say left, center, and right. So this is area 1, or we can call it also area left and area right of the bending moment. And we are going to say, okay, where is the centroid of this area? So maybe it's here. Okay. So we are going to call that X bar left. And the centroid here, I'm going to calculate X bar right. Okay. And we are going to say, actually the equation we are going to write, we say the moment of the left, which is the moment at A, which in this case is 0, but not in all problems. You might have a fixed support or an overhanging part, so the moment at A may not be 0. But generally speaking, we say the moment at the left times the length at the left plus, well, the moment at the center, I'm going to multiply it once by the length on the left and once by the length of the right, because they are, and we were going to say 2mc times L left plus L right, plus the moment at the, center, yeah, moment at the right times the length of the right. What does that equal? Notice that this whole equation, by the way, is divided by EI. But if we are using the same material to build the beam, E is constant. And if the beam is like the section is prismatic, then it has the same I. And there is no reason to, I can multiply right and left by EI and get rid with it, right? So basically, we don't write EI unless the I is different, for example, or the E is different. And in fact, even if that's so, we are going to, instead of dividing by E and 2E, and no, we are going to divide this part by 1, this part by 2. If this part of the beam has an E twice as the left, then every time I have L right, I divide it by 2, right? So it's like same thing for I. I can get a ratio of I1 to I2 or I left to I right and simply divide by that ratio. We are not going to see that in most problems. Equals -6 times the area of the bending moment diagram. We call it A sub L and A sub R. So A sub L times X bar L over the length L minus 6A right X bar right over L right. And that's the equation. You say, oh my God, it's so complicated. Yes, it was complicated in our times because we had to calculate those. Nowadays, you have tables that give you uh, they will replace this whole thing. If it's a continuous load, it tells you it's this. If it's a triangular load, it gives you this is the equation. If it's a concentrated load, it will give you that. Okay, and we may have to repeat it at C. Notice here, ML and M right are zero, so these two would cancel, and you will only have MC, and you can solve. But sometimes you have to apply it more than once if the moment is not zero at one of the two ends. Okay, let's take an example and see. I already drew the beam so that we don't waste time. Here is my beam. I have a fixed support at D. I have a roller at C and a pin at B. It really doesn't matter. It can be also a roller, so since we don't have horizontal loads, so Bx is zero. We don't need to write even an equation, sum of the forces in dx equals zero. We know that Bx is zero. So how do we start? Remember, I will start in the middle at C, right? You say, oh, but I have an overhanging part. It doesn't matter, because this overhanging part, you learn from statics that I can take the 100 kilonewton and move it parallel to itself at B, and at B it will be a 100 kilonewton plus a counterclockwise moment equal, or a couple equal to 200 kilonewton meter. So MB is basically negative 200 kilonewton meter. So instead of writing MB times L, I'm going to say negative 200. It's right here, right? Because I moved it, times the length of the left, which is 4, plus twice MC, which is unknown, times L left plus L right. They are the same, but we can write them so you can see that it matches the equation. Where did I place the yeah. So I have M left is negative 200 times L left, which is 4, plus 2 MC times L left plus L right, 4 plus 4, right? Plus MD times 4 equals. Now, instead of writing -6, the area, so instead of drawing the bending moment diagram, which in this case, by the way, I will show you how it's done. The bending moment diagram in the middle is WL square over 8, right? So W is 60, L square is 4 square over 8. Notice I have a -6, and then I'm going to multiply it by the distance of the centroid. Well, the centroid is in the middle, so x bar left is 2. Okay, so, and I'm sorry, I got this is the moment, right? But the area of the moment is 2/3 base times height. So it's 2/3 base, which is in this case L, in our case it's 4, times the height, and the height here is the bending moment itself, which is WL square over 8, right? So 16 over 8 is 2, so this would be 120. You see, you have to do the math and then multiply by 2 and then divide by 4. It's too complicated. So instead of that, they told you use W, which is 60, times negative, of course, W times, which is 60, times L cubed over 4. That is then -6, the moment times the centroid, distance from the centroid divided by 4. Okay? And then for the triangular part, I'm going to say minus W, which is 80, times 4 cube again. But then I have to write by, multiply by the right-hand side. In the table, you will see that it's 7/60. And here it's 8/60. So this tapered part, the small part, is 8W L cubed over 60, and the large one is 7 times that. And that's basically how you write it. As I said, these you get them from tables. You will memorize them if you use them a lot, but really, so here I have 8 times 2 is 16 MC plus 4 MD equals, we are going to evaluate that. So I have -60 times 4 square, right? If it's 4 cubed over 4, it's 4 square, minus 7/60. Usually we write 7, doesn't matter, times 80 times 64, which is 4 cubed. And then I'm going to add to that. Notice these were negative, but when I move that, I'm going to add to both sides 800. So plus 800. Does that make sense? Yeah, I get negative 757.33. That's the first equation. Because I have two unknowns. So I'm going to rewrite. So here was the 3-moment equation at C. Here I'm going to write the 3-moment equation at D. Okay, so MC on the left times 4 MC, plus 2MD. There is no right, so it's 0. 4 plus 0. The left is 4, the right is 0, right? And then there is nothing on the right, so plus 0. We only have two moments, not 3 here, right? And that equals, notice this would be the same, except this is 8 instead of 7, because there is no other loads. Because when I do a D, the load to the right is 0, to the load to the left is 8 times 80 times 4 cubed over 60. So 4 MC plus 8 MD equals -8 times 80 times 64 over 60, right? Oh, this is 8, and I wrote 0.8. Probably I wanted to do it -8. So anyway, we can multiply by -10, and you get -682.667. So this is equation number 1. This is equation number 2. We can easily solve them because you see, why did I say, oh yeah, 8. Okay, you see MD here is multiplied by 4 and here by 8. So maybe I can multiply this equation by -2 and then add it to that. Or why -2? Just by 2 and subtract it. It's the same thing. It's the same thing. So when you multiply that by -2, you get -32 MC plus 4 is -28 MC. -2 times 4 is -8 plus 8 is 0 equals, I'm going to multiply that by -2 and then add that. 832. From here, we get MC is -29.714 kilonewton meter. Okay? Now I'm going to take MC and substitute it in any equation. Probably this is easier. So I'm going to multiply MC by -4 because I'm going to move it to the other side, right? So I have 4. That would be a small one, right? Let's see, times 4, and then I'm gonna, so times -4 because I'm gonna move it, plus the negative, and I'm gonna divide that by 8, right? So I get MD is -70.48 kilonewton meter. So now I found the middle moment as well as the moment here. So now I can find the reactions. Notice that when you find the reaction, you don't need to consider the whole beam. I can take the left part and replace the right part by the moment at C, or take the right part and replace also MC by the moment at C. So I can do the following, but I cannot do that to C. Why? Because if I took this part and calculate the moment at C, I'm sorry, the reaction at C, I still have another reaction at C. So both of them add up to C. So best way is to find dy from the left-hand side, and then dy from the right-hand side, and then use summation of the forces in the y equals 0. It's much easier, right? So on the left-hand side, I have 100 kilonewton at A. Here is By. Oops, it's not that far away. By, it's 2 meters. And then there is C. Of course, there is Cy, but I'm not interested in it. Okay, let's say Cy left, because that's not Cy. There is another part that comes from the right-hand side of the beam. Both of them will give me Cy if I wish. Or I can, if I have time, I can use that to check my answer. But basically what I have here, remember, on the MC is -29,714. So all what I have to do is to take summation of the moment about C equals 0. I have 10 times 6 now. Okay, 10, 100. Why did I say 100 times 6 is positive, minus 4 By is negative, plus 4 times 60 times 2, which is the distance of the centroid, and finally minus 2974 equals 0. Notice if I move the 4 By to the other side, I'm going to say 600, so I can say 4 By equals 100 times 6, 600, plus 4 times 60 times 2, minus 2974. Did we miss anything else? I don't think so. And then I'm going to divide. So By equals 262.57 kilonewton, positive, meaning we assume it was up, and it's correctly up. That's how I find one of the reactions. Now I can do the opposite. I can take that part of the beam and here I have a moment that was -70.48, and here there is a moment that is 29,714. Notice it has to cancel that. It has to be equal and opposite. And that is Cy right. And this is the one I want, dy. Oops. meter, and this is dy. So I'm going to take again summation of the moment about C. Okay, now let's take the moment about C. So we have only this plus the moments, right? So I'm going to say 4 dy, that's positive, minus, because the distributed load, the triangular load is rotating clockwise, so minus 1/2 base times height. And notice that the centroid is at 1/3 and 2/3 of the base. 2/3 of 4 is 8/3. Then we add 2974. Then we subtract 48, because this is counterclockwise, this is clockwise, we equate to 0. So I'm going to move all of that to the other side. So these would be positive and that would be negative. I'm going to say 1/2 times 4 times 80 times 8/3 minus the 20. I typed 2974. It was better to select the whole thing. And then, oh, no, since it's negative, then I'm not going to subtract, I'm going to add. And then I'm going to add the 70, it's negative, so minus, oops. Oh, there is a negative here. Why I didn't delete the negative. I wanted to add it, so there is no positive. No, there is another one, right? Yeah, there's, oh my God. Did I have two negative minus? No, guys, okay. Let's say 1/2 times 4 times 80 times 8/3. And then we want to subtract the 29, so plus, because it's negative. And then I want to add this negative 70. So yeah, it's the same. So why it's giving me error? No, it's fine. Did I? That should be positive. Oh my God. Why did I say negative 0.5? The reaction has to be positive here. What else did I do wrong? Okay, let's check. Yeah, this is positive, this is negative, this is positive. So that should be fine. And then I'm going to divide it by 4. So I get, okay, that makes more sense now. dy equals 116.86 kilonewton, also positive, so it's up. And finally, I say summation of the forces in the y equals 0. I have negative 100 plus by minus 60 times 4 plus cy minus 1/2 4 times 80 plus dy equals 0. So when I calculate cy, I'm going to add all these three and then subtract the reactions, right? So cy would be 100 plus 60 times 4 plus 1/2 4 times 80. And that's happened to be 500. So I'm going to subtract dy, and then I'm going to subtract the 262, which was the by. Oh my God. So cy is 120. Does that make sense? Yeah, if they add up 120.58 kilonewton. Okay, so let's get now, we can draw the shear force diagram and the bending moment diagram. Let's draw the shear force diagram. Shear force diagram. I go down 100 for a distance of 2 meters. Again, we don't have time to draw anything to scale. And then I'm going to go up by, but if I subtract 100, then I will go up to 162 and a half, right? Or 0.57. Let's say this guy is 162.57. Then I'm going to go down 240. So we can do, first of all, we had 240. In fact, minus 100 because we already were below. And then plus the 262. Oh my God, I have to go back a lot because of that error. No, that was negative. See, this is negative and that's positive. So just, I'm going to delete those and write that. What's 2400? It's 240, right? So if I say 240 minus, because I'm going down, so it's negative 240 plus 162, that will take me, no, I said minus, oh my God. I'm sorry, guys, it's crazy. What am I doing? 77.44 kilonewton. And then I'm going to go up CY. So plus the C, let me first, okay, let me clear what we had here, this thing, just so we don't have a lot of, in fact, I don't need the 500. I don't need this thing and the error, just so it would be easy to reach those values. Okay, so I am at negative 77, and then I'm going to go up CY. So plus the CY was the 120, right? 120.57. So I'm going to say this plus 120. I will go up to 43. 43.14. And then I'm going to go down, but in a triangular, so it will go down something like that. Let's see. How much did I go down? Minus 1/2 times 4 times 80, right? So I get to negative 116.86, which is basically exactly dy. Okay, so I'm glad I didn't do error. Notice the 77 is below the 100. I told you I'm going to do it fast so we don't waste time. So here is my shear force diagram. Of course, if I have time, I will draw it much better by using a scale, some scale that makes it easier. Okay, now if I have the shear force diagram, I can draw the bending moment diagram. And notice the bending is the integral of the shear, integral meaning the area under the curve, So I can easily find areas, add and subtract them, and see if we will end up with the correct numbers we have. Okay, so let's start. The shear is constant in the beginning at 100, meaning the integral would be linear. However, yeah, I will go from 0 to 200. And then you would say, okay, how do I find this area? I don't know the base. Yeah, I will show you how easy you can find that. I know that this total distance is 4. And the ratio of this to that is the same as the ratio of this to that. However, it's much easier to divide this distance or this value by the sum of those, which was 240, and then multiply by 4. So I'm going to say 162.57 divided by 162.57 plus 77.44, basically is 240, and then multiply by 4. That will give me that distance. Subtracted from 4, I will get that distance. So let's see how we do that. Oh my God. And again, it's not important what you write. You are going to use what's in the calculator, right? So I'm going to go to 162, the 162 that we found. Well, I didn't write it, but yeah, it's 162 here. We had the 262. So I'm going to take this and subtract 100 from it. Remember, I went up to 62. Okay, so this is the 162.565. I'm going to divide it by the sum of the two, which is 60 times 4, or 240, and then multiply by 4. I get this distance is 2.7. 4 minus that is 1.3. 1.29. I'm going to write 1. This is horrible. And then how about those? You can divide, but square and divide. Okay. The best way to do it, because this is a second degree parabola and maybe some of you are not familiar with how to deal with it, it's much easier. I'm going to add and subtract a rectangle of this amount. What do you mean? I mean that if I add 116.86, that would be 0. And when I add 116.86, that would be the area of the weight, which is 160. So I will get a parabola that looks like that. And where is the 0 where I will get the maximum moment? It's basically 116.86. So that's the height. I should write it here. And this is 160. But notice, if I added 116.86, I have to subtract 116.86. You said, but I still didn't get the distance. Easy. This over that, this square over that square is this over that, because it's a second degree parabola. So I'm going to say, okay, 160. No, I don't like that. I'm going to say this doesn't matter if it's, because I'm going to square it anyways, divided by 160 square times 4. And that gives me 213. So that, notice I did this over that, so I get this over that. So this is 213, and that would be 187 or 186 something. 4 minus that. 187. Okay. Now, so in order to increase, I will get, let's calculate the value. So I am at negative 200, right? Negative 200. Then I'm going to add 1/2 times the base, which is 2.7 that we found here, times 162.57. Again, I can type it. So I go up to 2023. 2023, a moment of 2023, and it goes in a second degree parabola, 2023. Then I'm going to keep going down. Hopefully, what will I go to? Hopefully, I go to this value, right? Because that's MC. If I did my math correctly, I did a horrible work here, but we'll see. So I'm going to subtract 1/2 times 7744, which was a while ago. Oh my God. But it's already negative, so I'm going to, what? What is that? Yeah. Let's delete the negative because I multiply 1/2. I subtracted 1/2 times this times 1.29. What? Oops, not this. I deleted the 7 by error. Oh, something is wrong today. Times the 1.3. Where is the 1.3? Oh, 1.29. Whatever. Nice. Negative 29.7. I didn't get 714. Do you know why? Because previously I typed a number instead of selecting it from the memory. Again, it's not a big deal. So we say, okay, we're going to go down to negative 29.74, roughly. It's not exactly, but if I go back, that would waste your time. If I go back and instead of typing, for example, 15.4 or whatever the number was, I get it from the memory, it will get exactly like that. It should. Okay. Here I have a problem. How do I get the moment at this point? How much do I add? Listen to me carefully. The area of a parabola is 2/3 base times height. So what I'm going to do is to multiply 2/3 base times height. That will give me this whole area. And then I'm going to subtract 2/3 base times height. So I got that. And then I'm going to subtract this rectangle, 116.86 times that. So 3 steps. Here is my number. I'm going to add 2/3 times 160 times 4. That will add all of that. I don't need to find all of that. I want it only here, till here. So I'm going to subtract 2/3 base, which is 213, times height, which is 116.86. That was a while ago. Oh my God. Again, there is a negative sign. So let me delete the negative sign. That's not the end of the story, because all what I did is I added all of that, then subtracted this. So now I added that. But it's not this. I have also to subtract the bottom because I raised it by this much. So minus, no, I'm not going to say minus since it's already written as negative. The 116 was negative. Oh my God. So plus negative that times 187. Oh my God, a lot of work. Oh, 187 is here. 1261. Are we doing it correctly? I think so. It's negative 29. I added 2/3 base times height, 160 times 4. Let me check again. Then I subtracted 2/3, 213, which is the base, times 116, which is the height. And then I should subtract 116.86 times 187. Okay, so I go up in a 3rd degree parabola. Again, we don't know how to draw that properly, but we are going to go up to 12.61. And then I'm going to add this piece and subtract that piece. Okay, so I'm going, oops, no, forget about that. We already have this. So I'm going to say plus 2/3. You know what? I'm going to say 116.86, so I don't waste your time, minus 116.86 times 213. So I added 2/3 of it and subtracted the whole thing. So it's as if I subtracted 1/3 of this area. Negative 70.36. Yeah, it's 0.48. And I told you again, because of some approximation errors. I didn't want to go much longer. But the idea, I mean, drawing the shear and the bending moment diagram, we already went over that. It's not the big deal. The big deal is how to find the moments that would allow you to find the indeterminate reactions and make the beam to be statically determinate. Now we know everything about it. We know all the forces, we know all the reactions, so it's very easy to calculate the shear force diagram and the bending moment diagram. Again, sorry it took so long, and there are a lot of pitfalls along the way. But again, I hope you understood it. And if you have any questions, please don't hesitate to let me know, and I will get back to you as soon as I can. Thank you very much for watching. Have a great day. Hope to see you soon.